Final round. Fight!
Yo, yo, yo. Welcome back to the YouTube channel, bruh. It's your boy, Wiki. You know what it is. Yeah, man. We finally made it. The last one. Before I even get to what I need to get to, shout out to the homie Musa, bruh. If I'm not mistaken, I'm gonna shout his YouTube channel out. His name is Abavis Lord, if I'm not mistaken, bruh. Had a conversation with the boy, and we just spoke about the YouTube grind. And then I think one thing that resonated with me was like, do what you love. That was one thing he said, and I was like, let's go, man, because I'm hella passionate about what I do here on this channel. Thank you for being with me today. Just leave a like, leave a comment. Don't forget to share and definitely subscribe. I think I'm gonna start setting targets for the views. Number one, we gotta set targets for the views. We gotta set targets for the comments. We gotta set targets for the likes. So we keeping it easy. We keeping it simple. 5 comments, 5 likes, 5 subscribers, man. Each and every time we drop a video, we gotta get some new people up here. So yet again, let's go. This is the finalizing of what we've been doing so far, covering graphs, covering their traversals, covering how we go about constructing a graph through adjacency lists and adjacency matrices, also known as just normal adjacency matrix, right? And going back to the exam scope, bruh, I overstudied because it's like we actually only have to do up until the adjacency list and adjacency matrix and looking at the minimum spanning tree. So I'm gonna cover that, but just as a little bonus to you guys, shout out for being here, number one. So I'm gonna try keep it as short as possible today. We're just gonna revise a little bit, cover some concepts that we definitely need to know in terms of working with graphs. Then I'm gonna jump right into the adjacency list and a little bit into the trees. I don't want to make this a little bit into the trees. Pause. But anyway, I'm not trying to take your time. Each of these videos, I keep on saying like, bruh, keep it short, and then I'm like, boom, 20 minutes. So if I make this 20 minutes, that means this 3-part series is a little bit over an hour, and I hope it's worth your time. So without further ado, get it. So yeah, this is what we went over last time is about understanding how we would construct the graphs in our code. And primarily the means in which we do this is through utilizing the fundamental concepts that we've picked up so far from other data structures, primarily primitive data structures like your two-dimensional arrays, your one-dimensional arrays, just for constructing basic essentials. Like if you look at this adjacency matrix representation, we have rows and columns which can be then constructed using a 2D matrix, right, or a 2D array. And from that point onwards, we also have to understand the importance of these variables right here, because anytime I see undefined or clearly undefined variables and we are working with data structures and algorithm, these are usually known as our pointer or reference variables as to how we're going to conduct the process of putting things together. So I'm just gonna jump right in. Like in this graphs implementation, I just construct a simple class called graphs, right? And then I have a method that adds edges to our matrix. So we have our parameters, the 2D array, integer I, integer j. So when we construct this, we say I and j, right? So we're placing all the variables within this two-dimensional array by the rows and by the columns to 1, and vice versa by the columns and by the rows to 1. And the process of displaying your matrix is as simple as understanding that we're iterating through each and every single block. So I would say, right? Since it's a two-dimensional thing, it's like a two-dimensional storage. So you storing by the columns and by the rows themselves. So when I jump into this method, I say public static void display matrix, and the only parameter that we're putting into this method is the 2D array itself. And then in this first iteration, I'm like, for all the individual rows in the matrix, right? So I'm iterating through each and every single block that's occurring within our matrix. And then I construct a variable here called value. I just called it val, but value works. So for all the values in the rows, right? Print out those values and system out print line. And then the process of actually using this would be instantiating big words, man. But anyway, we're instantiating vertex with 4, right? Just a normal integer containing the value of 4. And then we construct our adjacency matrix, and then we pass the values into the two-dimensional array. So we're going to have a 4 by 4 grid situation happening, and then we just add our edges according to the parameters of the method, where we say this is our box, this is our storage, and place this value here and this value here, just to simplify things, right? And then we just display that. And then when working with the adjacency list, the main difference that we have to think about is the functionality of a, excuse me, the functionality of an adjacency list primarily works in the sense that we are kind of working with a linked list, and keep in mind the quotations, because it's like we have to consider that we are going to display the vertex and then the edges that are connected to that vertex. So like this whole three-part series has been building upon those same words. It should be taking a little bit more, just saying that these are the paths that connect to this one point, so on and so on and so on. So that's how we would go about defining that. And I studied, bro. Like if you look here, I have the notes for the breadth first search and the depth first search, right? So the interesting things about these searching algorithms is that the manner in which they function, you need to like put on your thinking cap a lot, because when I look at the two main points that I have for understanding how the breadth first search works, to put it simply, I'm like, number one, the exploration of the BFS. We have to establish the condition that states while the queue is not empty, we dequeue a node, and then from the queue, like we dequeue a node from the queue and visit the vertices of the node that we're currently working with. So a way I could paint this picture, right? It's like, let's say we have, yeah, we have a vertex. We just have the objects we've been currently working with. So it's like, I have this vertex. I push it into the position. I identify all the paths that are connecting to this vertex. I capture that like the data, and then I dequeue it, or I do away with that value, and whatever was next to that vertex will come in that box, identify all the edges, take it out, so on and so on and so on. So we enqueue the neighbor into the queue, and then we mark the neighbor as visited. And this is the process of noting that we are marking the positions of the index that we have visited, or of the vertices that we have visited. And then number two is the termination of the process. In order to terminate the process of running the BFS, we have to conduct the second process of the exploration of all the other adjacent vertices to that one that I've been talking about. It's like I put you in a box, identify your neighbors, take you out, and whoever's next, I do the same for each of those vertices. So that's the process of conducting the breadth first search. And in order to terminate the process of running the BFS, we have to conduct the second process of the exploration of the adjacent vertices. This will have this will have to involve the process of recursion and setting the base case, as the while loop checks whether the queue is not empty. So while we haven't run out of vertices to explore, continue to perform these functions. And I would like to go into this like fighting, but it would kind of be a waste of your time, considering that I'm primarily making this for the second year students who are studying ADF currently. So I will update these videos. Definitely will have to, but this is just from me to you in understanding what the fundamentals of what we're going to be writing about are. And yeah, that just covers BFS and DFS, right? Cool. And then jump into number, yeah, this is number three to me. Ooh. But anyway, once we jump into this portion, right, working with the minimum spanning tree. Okay, cool. What is a minimum spanning tree? So when you ask that question, I would answer it by saying, since we have a graph and all the edges of the graph have been weighted, we want to then find all the paths that connect the pieces of land I'm gonna reference back to the Königsberg Bridge problem. Like I'm just gonna say we are going to find the minimum distance it takes to get to all these pieces of land minus all the we're not gonna have all the edges, but we definitely are gonna have all the vertices. So it's kind of like saying find the shortest path from A to B. As simply as that. So with the minimum spanning tree, we have to consider that we are working with a weighted tree. So all the edges have values assigned to them. Pardon my tongue slipping. I'm tired. It's been a long day, kind of, but bear with me. So we have to consider that we are going to apply the traversal algorithms that we have for the graph above, and we will work with the subgraph of the initial graph. If the subgraph or the subtree should have made a fix there. If a subgraph has all the vertices of the initial graph, we would refer to that as a spanning subgraph. But since now in this instance we are removing the edges, the graph is no longer connected to its entirety. It is, but it's not forming a circuit, because as you can see with this graph over here, it's like we can go in a circle around all these vertices and come back here. But now in our case, let's say we remove number 7, since it's the largest value, right? We remove number 7, we can go to all of these vertices, but we don't have that path anymore. It'll take too much time, the cost would be too much to travel. That's the way in which you would visualize working with the minimum standing tree. So I'm just gonna make a little comment over here. Cool. So working with the MST, we have to then find the total weight of all the edges of the graph, and with that, we must ensure to find the path that contains the smallest values that still allow all the vertices to be connected. Going back to what I said, it's like we're trying to find all the paths that connect, but we don't want to take in the one that has the largest value. We like find the shortest route to all the paths, but take away the edge that weighs the most. And yeah, I don't want to say I don't want to go into depth. It's just more so like simplifying the process of understanding what we're working with, because I don't want to make this video long, so I've already said that. But anyway, pardon me. And then the algorithms behind the minimum spanning tree. So we're primarily working with two algorithms. It's the Kruskal's algorithm and the Prim's algorithm. I haven't covered Prim yet, but I have touched on Kruskal. It's very dense. I won't even lie to you, bro. I'm still a little bit dumbfounded by it just because there's so many components interacting with each other, because number one, we have to consider that we're working with inner classes or classes within a class, and this is not even inheritance sake, right? I mean, we are able to implement inheritance and have all those functionalities extending to each other, but that's not what we want in this situation, because we are not extending the functionality, we are bringing it all together. So these are different objects coming together to serve one purpose. So this algorithm is known as a Grevia algorithm, which implies that we're ensuring that the algorithm builds the solution piece by piece. And its main functions follows the following steps. We sort the graph according to their respective weights. So we are going to sort this graph according to the weights of the edges, right? So from number 1 all the way to number 8, from the smallest to the largest, right? And then step 2, we start the iteration to find the spanning tree, and with each inter with each which with each iteration, we add the next lowest weight edge one by one. Then number 3, we pick the smallest edge, and we ensure that we don't form a cycle. If we don't have a cycle, then we add that edge to the minimum spanning tree or the data structure that we are working with, because I'm gonna get to that part, but we have to understand that we have to store all these values somewhere. That's the main point. Not necessarily the main point, but like understand that we have to store these values and then display them. And then number 4, we repeat the process until there aren't any vertices left in the graph. Pardon me for that. That was a bit nasty in it. But yeah, let's just take a little breather first, man, before jumping into that. That was quite a bit of talking I did. I mean, I'm the only one, but I feel like this should be a two-way conversation. So just understanding like our main focus, as I said, is trying to find a route that traverses all the vertices, but we have to take out the fact that we don't want the largest vertex or the largest edge to be included. We want a complete path, but it shouldn't be a circuit. It's like we shouldn't be able to go around in a circle, but like all those vertices needs to be connected. I hope you're still with me. I hope you're still with me on that one. But anyway, let's jump right in. I have this weighted graph over here. And then I'm like, using this weighted graph above, let's conduct this algorithm with a dry run. So first things first, right? We said that we have to sort the edges. So another part that we have to think about when working with the minimum spanning tree is that we don't only have the weight of the edge, right? But we have to take into consideration the source and the destination. So it's another way of saying that we are working with the paths, but I don't want to work with unnamed paths. You feel me? Let me use a little hand language over there, but we have to consider that we're going from point A to point B. I want to go from my house to your house, but I need to know what street to take if you're still with me. So, when we are sorting the weights of the edges within a graph, we have to sort them in their order or ascending order and have to take into account the consideration of the source and the destination vertices. So in this graph, it contains six vertices or like six of these dots, right? And seven edges, seven of these paths right here. And our goal is to then have 7 minus 1 edge, 7 minus 1 or 6 edges in our minimum spanning tree since we're gonna delete number 8. But he doesn't know it. Since we still at step 1, he's still like, I'm good, but no, he's not. So we have weight number 1, source and destination. So what that would be, weight number 1, 1 would be our source, 2 is our destination. We could also have this the other way around because it's like it's an undirected graph. We haven't specified in which the paths flow, the way in which they flow. So we could have it as this is our source and this is our destination. It doesn't really matter right now because in the end, our algorithm is going to then point out the path that connects all these vertices and leave this one out. Cool. And then I just carry on stating the weights, the source, and the destination. And then point number two is selecting the smallest edge of our MST. So once we have sorted our minimum spanning tree, we are going to start by weight number one and then chart it according to its source and destination. So it's going to be source one, source two. And then we're going to come into the second weight, right? Which is number two. And then source two and destination three. So you can already see that we have 3 points that are connecting. So excuse me, that's what is meant by a greedy algorithm. We're going to do this part first, and then this part, and then this part, and then this part until the bigger picture comes along and we have our minimum spanning tree. So I just define these are also important actually. The packages that we import are highly important because it shows here that we have an array list and a list. But the one that was really not tricky, I have used the comparator before, but it's just understanding that we want to compare the conditions, right? It's in the name. It's like I want to compare. It's the comparator. It's the one that makes this decisions between the two. And then I jump in. I'm like public class Kruskal MST. We first define an inner class that contains all our data about our MST, such as the weight of the edges and their source and destinations, going back to how we had sorted over here. And then I just define an inner class within this Kruskal MST called edges. So this holds all the information of our edges, the source, the destination, and the weight of the edge. And then this is just the constructor. And then once we do that, we close off the construction of this object. Keep in mind it's an object, right? Cool. And then in our bigger Kruskal MST class is another class called subset. And this subset, as much as they call it subset here, it would have been, even though this is my code, I studied on Geeks for Geeks, but they have a tendency of making things a bit too much. So I just came here to simplify things for you, and thank you for watching. I hope you're still here. Don't forget to like, comment, and subscribe. But as you look at this public class subset, right, we have the parent and the rank, which had left me a bit confused because I was like, "What do you mean?" Since all the notes have been synthesized from that source, I was like, "Parent and rank," but we'll jump right back into that a bit later. And then another interesting thing about the Kruskal's algorithm is that we have to use um what is known as the let me find that for you. Sorry.
A few moments later.
Hi everybody. Well, I have to cut the video short because the software I'm using doesn't allow me to like do clips over 30 minutes. This is a warning that it's quite long. So it's not gonna be a three-part series. It's gonna be a four-part series. But I'm gonna cut it like halfway. Make sure you can grab your drinks, grab some water, and then we'll catch up in the second half, man. Peace out.